In Bayesian data analysis, it's possible to compute posterior distributions exactly when the problems are simple. But as soon as you start to get into some real-world complexity, the calculations get very complicated very quickly. Happily, there's an easy way to estimate complex distributions simply using computer simulations. First, we'll break down the complex probabilities into simple parts. Second, we ask the computer to flip a bunch of coins for us. You could try to get trained monkeys to flip the coins for you, but I don't think that they could count as fast as a computer. Anyway, we use the computer's coin flips to represent outcomes from the simple probability distributions. Next, we combine the simple outcomes from each of the simple parts into complex outcomes from the complex distribution we're interested in. Finally, we use counts of the simulated outcomes as an estimate of our complex probability distribution. To be a little more specific, if the complex probability distribution we're interested in is the posterior, we can break down the posterior into simple pieces using Bayes' theorem. The posterior is simply the likelihood times the prior divided by the marginal probability of the data. Each of these simple parts, the likelihood and the prior, is fairly easy to simulate. Next, we need a way to combine the outcomes from each part, the likelihood and the prior, into complex outcomes. For this, we'll use a technique called Markov chain Monte Carlo, or MCMC for short. The gory details of how MCMC works are beyond the scope of this class, but let's see if we can understand the gist behind the madness. And for that, a story. Jack and Jill went up the hill every single day. "Oh, Jack," said Jill, "I'm tired of going up this hill. It's so boring. Can't we make fetching water any more interesting?" "I know, let's play a game," said Jack. "Instead of just going straight up the hill, let's flip coins. Each time we get a head, we'll take a step up the hill, and each time we get a tail, we'll take a step down the hill." "Jack," said Jill, "we'll be taking one step back for every step forward on average, and we'll never make it up the hill to get water in time for Ma to make soup for supper tonight." "Okay, fine," said Jack, a little indignant. "Let's make it a little more interesting. We'll still flip a coin to see whether we go up or down, but if the coin comes up tails, before taking a step down the hill, we'll flip the coin a second time. If it comes up tails again, then we'll go ahead and take that step down the hill, but if it comes up head the second time, we'll just stay put. That way, we're more likely to make progress up the hill, but we still have a chance of going backwards just to make things interesting." "Let's give it a try," said Jill. And they started flipping coins and taking steps forward and back on the hill. They must have looked pretty silly to any passers-by walking up and down the hill like drunks, but they had a splendid time at it. And because they set up the game so that they were more likely to go up the hill than down, they ended up spending more time toward the top of the hill, where the well was, than at the base of the hill, which was far less interesting for drawing water for supper. The story with Jack and Jill illustrates Markov chain Monte Carlo, which, as the name suggests, is a chain of steps through parameter space, that is, through the space of all the possible models. The steps from one possible model to the next are all random, but the jumps are set up in a way that you spend more time with models that are more plausible, and less time with models that are less plausible. Jack's game is very similar to a common algorithm for MCMC called the Metropolis Hastings algorithm. In this algorithm, you first flip a coin to determine whether to go up or down in the parameter space. This is called the proposal distribution because it proposes what step you should take next. If the proposed model is more plausible than your current model, you take the step. But if the proposed model is less plausible than your current model, you flip a second coin to determine whether to actually go through with the proposed step. This is called the acceptance probability. In the Metropolis Hastings algorithm, you accept a less favorable step in direct proportion to how unfavorable it is. You accept slightly unfavorable jumps much of the time, but you accept very unfavorable jumps only rarely. The result of all this jumping is a record of all the places you've visited along the chain, like a video of how far up the hill Jack and Jill were at each point in time. Like Jack and Jill, you may start very far away from the most plausible model, but once the chain gets going, you'll end up spending most of the time around the most plausible model, and proportionally less time with less plausible models. In this example, the chain started near 0, but the most plausible model is around 60%. After a few steps, the chain arrived in a region near the most plausible value and stayed there. If we waited long enough, the chain would get back down towards 0, but this would be pretty rare. Since it takes a little time for the MCMC chain to arrive in the region near the most plausible model, we typically throw out the first part of the chain to make sure that our results are accurate. The part at the beginning that we throw out is called the warm-up, or the burn-in period. The rest of the chain represents simulated draws from our posterior distribution. If we make a histogram of these draws, we'll have an estimate of the shape of the posterior distribution. In this example, we see that values just above 60% are the most plausible, and values near 20% are not very plausible at all. We could use the mean, median, and mode of the values from our MCMC chain to estimate the mean, median, and mode of the posterior distribution, telling us which models are most likely. And the standard deviation of our MCMC values estimates the standard deviation of the posterior distribution, which tells us how confident we are in our most plausible